here. So we will be starting the webinar very shortly. All right, everyone, if you're just joining us, we are just waiting a couple minutes for everybody to log in. We will start very shortly. Thank you for joining us. Alrighty, I think maybe we'll start getting started as people still come in. Good day, everyone. Thank you so much for joining AMSC's webinar. This is the Core Power Engineering, applying IEEE 519-2022 limits. My name is Wes Dyson with AMSC's marketing, and I'm joined by our senior technical staff engineer, Chris Duffy. Before I introduce him, I'd just like to draw your attention to a few things. I see some of you have already found the chat there on your right-hand side. I'm going to go ahead and put my email address in there now so you can see. That is where we will have you interact with us and ask any questions during the webinar. We do ask that just because Chris is the only one presenting today, to hold all your questions till the end so that he can get through them. But if there is anything pressing that you want to call our attention to, you can certainly use that. And if you experience any issues during the webinar, you can certainly email me there if you need to get in contact with me. Generally, because this is a web-based webinar platform, the main first line of defense, I should say, is just trying to use another browser. Sometimes that helps if there's any skipping or anything like that. But hopefully nothing occurs. So we're expecting this webinar to run maybe 90 minutes, maybe a little bit over. And again, just if you could hold your questions until the end. Oh, also, if you need any professional development hours for today, we're happy to certify your attendance for that to verify that you were here. But it is up to you and your individual programs and states to make sure that will work for you. But we are happy to verify that you attended for the 2 hours today. All right, so let me introduce Chris. He is a 38-year veteran power engineer, cutting his teeth at Power Technologies, Inc. in Schenectady, New York, starting in 1985. He was introduced to power system harmonics while working for Ray P. Stratford, co-chair of IEEE 519 standards, 1992 update, and was the secretary of that same document. In 1995, he took a position at Electrical Systems Analysis in Oregon, where he consulted and maintained the Easy Power software engines. Chris is, as I mentioned, our senior technical staff engineer here at AMSC and a licensed professional engineer in Oregon. He joined our network planning team in 2022, performing system analysis for the DVAR and DVAR VVO StatComs, Neeltran rectifiers, and NEPSI harmonic filter product lines. So he is absolutely the right person to be doing this webinar for us today. We really thank you for being here. Chris, why don't you go ahead and take it away?
All right, just let me know that you can hear me well.
Sounds good to me. If anyone wants to mention in the chat, if you can hear us okay, that would be great.
Yeah.
Hopefully you can hear us after all that introduction.
Good, yes. Okay, well, I'm glad all of you are here today. Thanks for attending. And I will just, for the people on the East Coast, since we are talking about standards material and you just got back from lunch, I would suggest a stiff cup of coffee for this one. Because yes, we're going to be reading content out of the standard significantly here because it's actually fairly well written. And so there's a number of paragraphs there that are very descriptive that we can use. So as I go through the slides, let me click on the next one. Okay, there's a quick legal notice that when you get the copy of the slides, you'll see that up front. But the key purpose of our presentation today is to educate and share the technical knowledge we have with attendees. The webinar is going to cover the basis. I think this was specified earlier in the invite. Basis for limits, methods to measure, percentiles, which are important for this version of the standard, and application of harmonic voltage and current limit tables, and the use of IEEE 519 possibly as a regulatory document. The webinar will have a live presentation that I'll do at the end on how you can actually perform a compliance for a measurement, and then also for an actual study that you could possibly perform. So a number of definitions are needed to help us get through the standard, and let's talk about each one of those. They're listed here. So fundamental, I'm sure a lot of you already know this, but let's at least put it down here in a slide that fundamental is the fundamental driving frequency, or for us, typically 50 or 60 hertz, depending on where you are. And in the United States, of course, 60 hertz. Fundamental voltage is also called V1 often, if you're looking at a chart of harmonic distortion, a spectral chart, and same thing for current. RMS and root sum square are basically the same number when you have all of the harmonic frequencies accounted for. And so we call root sum square, obviously because of the shape of the equation, as the square root of the sum of the squares of all the harmonic components. And as I noted, that will be exactly equal to RMS as long as you've included all of the frequency components within that summation of all those squares underneath the radical. And that's also true for current. We call that root sum square for current. Total harmonic distortion, I'm sure many of you have seen the equation. Square root of the sum of the squares of all of the harmonic voltages. Notice the difference between this one and the last slide is simply the first harmonic, which is not the correct way to say it, but the fundamental V1 has been removed from the VTHD, ITHD in these equations. Now, these equations thrown up here are in volts and amps. If you want to put them in per unit, you would divide them by the fundamental voltage, or V1. And then if you want to put them in percent, you just simply multiply by 100%. Okay, let's go to here. So for total harmonic distortion, VTD, THD, and ITHD have an inherent weakness, and that is when their fundamental values get near zero, then you get an amplification of error and an amplification of small values that just may be noise. And so one of the key things that we need to do, and that we're going to talk about next, is that we need a basis by which we can calculate total harmonic distortion for voltage and current. And so what would be the best thing to do to make them an accurate figure of merit would be to determine what that basis is. And that's been done for us in the 519, and we'll discuss that in more detail. But basically, we're going to choose what our maximum demand level is, and then we're going to per unitize or percentize all of our harmonic distortion values on that demand basis. So it's called maximum demand current in the 519 standard, and it offers a solid basis for calculating harmonic current distortion. And the same thing is done for voltage, and we typically use the rated fundamental voltage for that. But for the maximum demand current, according to 519, let's just read this quickly. I think this will just answer all the questions as to how it's defined. IL, maximum demand current, is established at the PCC and shall be taken, PCC we're going to define also, that's the point of common coupling, and shall be taken as the sum of the RMS currents corresponding to the 15-minute or 30-minute maximum demand during each of the 12 previous months divided by 12. So you can see it's an average of the maximum demand values for 12 months. If 12 months of data is not available due to the length of time, then the maximum 15-minute or 30-minute apparent power demand for each month should be summed over the total number of months available and then divided by the number of months. Again, that's just telling you that what we want is an average of the monthly maximum demand to define maximum demand current. Here's another, just reading the paragraph continuing. For situations where the installation is a proposed new installation, like it's a greenfield project or it's on the drawing board, IL shall be based on the projected monthly maximum demand. Okay, so you need to come up, you run your power flow, your loading analysis, after getting all of your data established for your loads, and then you're going to determine what the projected 15-minute or 30-minute monthly maximum demand is going to be. So we're going to call this new value, and this is used within the standard, demand distortion. So we're going to rename it from ITHD to ITDD, or demand distortion, and we're going to take that same radical with the accumulation of the squares of each of the harmonic components and divide it by IL to achieve ITDD. Now, and by the way, that can now be compared when it's performed statistically against the IEEE 519 current limit tables. Now, you can also rewrite that equation. You can take an IL and bring it up into the radical, and you can see each of the harmonic components. Now, here we have second, third, and fourth, and each are put in per unit now. That's not multiplied by 100 yet, but they're in per unit. And if you take those values and break them out and multiply them by 100, then what you find is this component is what you can now compare against each of the limits that are within the table. So we take each harmonic now, we divide it by maximum demand current, and that gives us a percentage which we can now compare against the values within the tables. And this has to be done statistically, and we're going to talk about that. So let's update VTHD. The standard doesn't take any initiative to rename it. And so we'll just continue to name it VTHD, but now we'll divide it by the nominal voltage for the system. For instance, 13.8 kV, 34.5, etc. for your measurement. If the voltages are line to neutral based, you would then divide them by the line to neutral nominal voltage. And this now can be statistically compared against the 519 voltage limit tables. Now, if you have a meter or a device that's calculating this based on fundamental, the difference is going to be very, very small, because typically the voltage at the bus where it's being monitored is, within 95 to 105%. So it's going to be very little difference if you actually divide by the fundamental at the time versus the nominal voltage. So the next item worth a definition is the symmetrical three-phase short circuit current. Important thing to note is that this is the current that is expected at your point of common coupling, and it should exclude both AC and DC decay. So it's a symmetrical value, and it's easily calculated from a short circuit Thevenin equivalent impedance at the grid. So once you get that information and you get the equivalent short circuit current, then that would be the value that you'll want to use. And again, it needs to exclude AC and DC decay, which are values that are typically incorporated and utilized in breaker ratings and then determining maximum offsets and maximum fault current for fuse protection and these kind of things. But we have to exclude that because what we're going after is a comparison of the size of the plant versus grid stiffness. That's what we want to use this for. So they base it off of the symmetrical three-phase short circuit current. Sometimes you may want to include more than one of these values, and that would be the case where you have a condition that can change grid strength. In other words, it has a normal operation, and then it has a weaker condition that may exist for a significant period of time. So if the weak grid condition is going to be around for a while, you need to make sure you're within compliance for that weaker grid condition as well. And so for that case, you may have another value of short circuit current for that weaker grid condition. So the scope and purpose of the standard is kind of revolving around a history. Okay, so let's look at some of that history. In 1981, the original version of the 519 when it came out had only voltage limits. In 1992, they added current limits, the point of common coupling, a discussion on the basis of how they came up with the limits, and a plethora of other informational content on harmonics. Now, in 2014, and there's a lot of things within the 92 version that were not necessarily controversial, but were misinterpreted. And so some clarification was needed. And when the 2014 version came out, it added that clarity to how you define the PCC. It removed all of the informative information that was in the 1992 version. It added a statistical approach to harmonic measurements and limits, and then clearly noted that the standard was not to be applied to equipment nor to locations within a plant, and that was not within its scope. And finally, in this latest 2022 version, it transitioned, this is a big deal now, the IEEE 519 from a recommended practice into an actual standard. And I think there was some modification of the limits for even harmonics down at the lower orders. But that change from being a recommended practice to being an actual standard now has heightened the IEEE 519 into the same area that ANSI breaker standards are. So it's now an actual standard. So let's look at the scope directly taken out of the 2022 version. It established distortion goals for the design of electrical systems for both linear and nonlinear loads. We are introduced to the point of common coupling. That's the interface between sources and loads. Observance of the design goals will help to reduce interference between electrical equipment. That's the entire goal. That's the purpose of the 519, is that we're all going to share in this, and how much we have, capability we have to absorb the harmonic production. So if we follow the 519, hopefully that will reduce interference between plants that are nearby each other, etc. So users are directed to other applicable standards such as 1547 or standard 2800 for current distortion limits of inverter-based resources. That is not what we're going to discuss today, but we will at least look at there's a small figure within the 519 that helps you determine which standard you should be going to. So IEEE 519 addresses the steady state limitations. Transient conditions may exceed the limits, and that may be encountered, but we're talking mostly about steady state conditions of a facility. This document does not cover radio frequency interference, but there is some guidance offered in the back on telephone interference, which is kind of fading into the past, given we don't have those type of handheld systems anymore and lines overhead. The limits given in this document are based on assumptions that are technically justifiable where at the PCC, which is the point of common coupling between system owner, operators, and users. So the assumptions and therefore the limits in this document are not necessarily valid at any other point in the power system. I mean, technically they possibly could be, but that's not the point of the standard. The point of the standard is an evaluation only at the point of common coupling, not within a plant and not for any individual piece of equipment. For this reason, the limits given in the document are not intended, again, to be used for the evaluation of equipment. And forgive me if I just throw this big, bold slide up, but this was one of the biggest issues that came about from the 1992 version of the standard up to now. I am still, at this time, dealing with vendors who produce drive equipment that will put out a document that says we meet the 519 standard. And that is completely inappropriate because the 519 standard is not an equipment standard. It's not to be applied to individual equipment items. It is a system standard. And it is most likely going to be applied not at the bus where the drive is connected, but at a bus someplace else in the system where the point of common coupling is. The IEEE 519, again, is not to be applied within a plant. That's not its scope of use. Its scope of use is solely to be provided at the PCC. Now, that will not keep people from taking the 519 and trying to apply it within their plant. And you can get varied results. But again, that's not within the scope and purpose of the 519. So the PCC, the 519, it will be supplied or should be applied at the PCC. And by the way, forgive me if I'm swapping shall and should. We need to read it as it is. And if you go into the document, you'll notice that at the beginning of the document, they specifically define the difference between shall and should and several of the words that are within the standard. And I suggest you read it to make sure that you understand those differences. And I think shall here is basically more forceful than should. And I think that's the point that they're trying to make. Shall be applied at a point in common coupling between system owner or operators and users. The PCC is usually taken as the point in the power system closest to the user where the system owner or operator could offer service to another user. So it is the point up on the distribution supply to a user where other users can be connected as well. That's where you're sharing the system. And that is the PCC definition per the 519. So typically for industrial clients, this would be someone at a dedicated service. You know, the PCC is on the high side of that supply transformer. For commercial supplies, most likely on the common low voltage side where you're being billed. Though not stated in the 519, I have seen cases where the PCC has been known to be negotiated and or mandated by like a utility supplier, that the PCC, that it's going to be at our point of metering, for instance. And some of that is based on the historical definition of the PCC, where it has a statement or a clause in the earlier versions about often this is at a point of metering. Well, that's been removed now. That's not within the standard, but there is a historical precedence of that having been in there previously. So limits in the 519 are a shared responsibility for harmonic control between owners and operators and users. Users produce harmonic currents that flow through the owner's system, and everyone is responsible. And so this leads to the owner operators being responsible for voltage conditions, and that the users are responsible for current being put into the system. And we're going to draw that line very clearly. So when we get to voltage limits apply to owner operators, current limits apply to users of the system. Again, it's a shared responsibility. The limits were produced with some diversity and things included. Okay, but to maintain harmonic voltages below these recommended levels, all users have to limit their harmonic current emissions to reasonable values to determine an equitable manner by how they all share ownership, because they each have a stake in the system, the supply system. And each owner or operator will take action to decrease the voltage distortion levels by possibly modifying the supply system and the characteristics as necessary. So again, shared responsibility. Users limit their current, owner operators control the voltage distortion by doing what's necessary on the supply system to keep voltage clean. So in order, again, I'm reading these sections, and that's why I have this note here. So I'm referencing, that this is taken right out of the 2022 standard. In order to allow the system owner or operator to control, they have to make sure that the users don't cause too much modification to the actual impedance characteristic of the system. that is also important for users not to do. So in effect, such actions taken by a user that could result in producing excessive voltage distortion, that might occur when the impedance characteristic is unnecessarily changed on the grid side. That is why it's when we do harmonic filtering, for example, we always like to apply the filter on the secondary side of the main supply transformer. It gives us isolation, and that transformer is important for that giving and providing isolation between the two systems, so that what you do inside your plant does not modify the grid. So they're just saying that equipment additions that lead to undesirable conditions should be controlled in a manner similar to how we're basically controlling the harmonic current production being injected into the utility. So in summary, we establish harmonic limits for design systems with linear and nonlinear loads. The PCC is defined as that interface where we're going to do our checks. The 519, within its scope, defines the limits that address steady state conditions on a statistical basis. It notes that we can have short-term exceedances, that they may exist. The voltage distortion limits are provided for owner-operators. Current distortion limits are provided for users of electrical power. So let's shift down. Let's look at measurements, because there's two fundamental ways that most of us are going to use the 519. We're going to have a system that has a problem that is existing, and it has an issue. There's high distortion levels. Somebody's complaining. Maybe no one is complaining, but maybe a utility does a systematic approach where they look at conditions around their grid because they want to make sure everyone's in compliance. I haven't seen that very often. Most of the time, compliance checks don't occur till someone senses there's some type of a problem. But so harmonic measurements are one way, and the 519 is all set up for a compliance measurement. But at the same time, we do study work in advance to make sure that the system we're going to install and connect onto the grid will not violate the limits right out of the gate. That's one of the key things that we do in a system design. So for the evaluation scope, just let's understand that the 519 adopted in 2014 a method that's taken out of the IEEE standard for doing a statistical evaluation. And so the measurement evaluation must conform to this statistical evaluation method described in these IEEE standards, and the instrument must be a Class A instrument, and you can read what that means in terms of its accuracy class in the IEEE standard. The measurements should also be made up to the 50th harmonic at a minimum, and the measurement method must incorporate statistical evaluation based on 95th and 99th percentiles. So let's look at these for a harmonic measurement. And this may be the only time you ever hear this, and you may never want to care about it again in the future, but at least you've heard it once and it's been presented to you once, so that if it's necessary in the future, you can recall it, you can go back to it, maybe you'll get a copy of the slides, and you can say, you know, what is really going on here? And so for harmonic measurements, the 519 requires 12 cycles of measurement for 60 hertz, 10 cycles for 50 hertz, a spectral resolution of 5 hertz between each one of the frequency components. And then spectral values are going to determine by taking the root, the square root of the sum of the squares of the harmonic components that are on the harmonic and the 2 5 hertz away measurements or decompositions that are just to the right and the left. In my view of doing this, the values at 295 and 305 are rarely necessary if you have an instrument that is doing good phase locking. So if you have an instrument that really does a great job phase locking, you'll almost see no component in the 295 and the 305. But just in case there's an instrument that's not doing too good of a job and you're getting energy bleed of the harmonic into these two areas of resolution, they include this in the standard. So there's two major measurements that are necessary for the statistical evaluation. One is, I'm going to flip the slides here, very short time and short time. The first one, very short time, is created from 15 individual 12-cycle measurements at 60 hertz. We'll skip over the 50. It's just a different count because if it's a different frequency. But overall, we are looking at a 3-second value that's calculated. Okay, if you multiply those numbers, you'll see that comes out to be 3 seconds. So so you do this for each individual harmonic. And for example here, at the 5th harmonic, this will be the square root of the sum of the squares of 15 consecutive values, each one being 12 cycles at 60 hertz, divided by 15, you take the square root of that. You do that both for the voltage and the current. So this is a 3-second RMS aggregate of each individual harmonic. Now, for short time harmonics, they're going to do it over 200 short time evaluations. Okay? Or, excuse me, 200 very short time evaluations. So we're going to take these values, the very short time here, that are produced from this evaluation, and then we're going to aggregate them into a 10-minute value. And so we take this aggregation, we just square root of the sum of the squares of all 200, we take an average of them, so it's an RMS aggregate, and you're going to perform this at each individual harmonic as well. So how do we use these values? What the 519 will want you to do is to take the 3-second very short time values, accumulate them into a probability, and determine the 99th percentile. And I'll show you how this is done. It's actually trivially simple. It's not complicated at all. And we're going to repeat that for the 10-minute values that are accumulated into a probability. We're going to determine the 99th percentile, and then for the same 10-minute values, come up with a 95th percentile. Notice, the 519 offers no help in specifying this statistical process. They just expect you to know how to do it. Now, in the IEEE standard, you might find some things that give some description on this, but I can remember the content. There was some more detailed content within the 2014 version that talked about this methodology. So such methods should first employ the creation of a probability curve. And then from the probability curve, we're going to accumulate it into the probability distribution. And it's literally this simple. So let's say we'll do the 3-second values. It doesn't matter. You can do this either for the 10-minute values or the 3-second values. As time goes by, you're going to count how many are within a particular range of distortion. And here I happen to be analyzing total harmonic distortion. So between 0 and 1% THD, I only had, within my time of measurement, I didn't have anything happen there. Between 1 and 2%, I only had one time that I had a 3-second value. And here, between 2 and 3, I had 3 values. Between 3 and 4, I had 6 times that occurred. Between 4% and 5% THD, I had 10 times that happened. So when you want to calculate the probability, you simply take the number of counts and you divide it by the total number of counts, 45, and you see that's done here. So the highest one being 11 divided by 45 is 24.44. So 24% of the time, the voltage distortion was between 5 and 6%. And if we take these numbers and accumulate them up to 100%, so we take 0, we add 2 to 0, we get this. We add 6.67 to 2.22, we get this. We add this number to that, we get 22. This to here, you get 44.44, etc. on up. This gives us our distribution. So this is a trivial spreadsheet to create. And if you plot it, you actually plot the percent probability. Here it is. Remember, the highest value was 24.4, and that's shown here. And then if we accumulate this into a distribution, we have this, where we go up to 100% at the end where we've included every single one of the counts. The percentile is the location on the probability distribution where the percentile is at 95 and 99%. So the 95th percentile is this diamond here. And the way we get that value is we take the linear interpolation between the distribution from 7 to 8 and from 8 to 9. And similarly here, we just take the linear difference between these two. Now, this is a very coarse distribution. In reality, an instrument will include much higher resolution. In other words, it'll go between 5 and 5.1, 5.1 to 5.2, 5.2 to 5.3, etc. It's not going to be this coarse, but for illustration purposes, this shows us how we achieve the 99th and 95th percentile, and it's this simple. You just take a linear interpolation, which I've laid out here in equation form, and I've calculated the value for the 95th at 7.88. And if you go back here, follow it down to here, it's about 7.88 in here, okay, somewhere between here and here. Now, what I did was I assumed that the center value, the average value of this bin was 7.5, right? Because it goes between 7 and 8. Well, that's not fine enough resolution. So I say, well, let's say the bin exists at 7.5. And so that's how I did this percentile calculation. And then this one here, you'll see is 9.05, which correlates to down here, 9.05. Okay. Limit basis. Now, sadly, there was some content removed in the 2014 update that existed in the 92 update of the standard. There was a section on the basis of how they came up with the limits that are within the standard. And that, all the way from the 2014 to now, is gone. And so if you want to determine the basis for who and how and what they did to come up with those limits, you have to go back to the 1992 version of the standard. And even that presentation in the 92 standard was missing a lot of detail. But it's really all we have, unless you want to hunt down the person who was responsible for creating the limits and ask them, what exactly did you do for that determination? So it's the only material that we have at this time, if you want to look historically, that's documented, to talk about the formulation of the limits. But it does show the tight link between current and voltage distortion. In other words, it's saying, we're going to limit your currents for a reason. And the reason is, we don't want the voltage distortion to go above a certain level. And you can see that. If you look at the 92 version, it says, the philosophy of developing harmonic limits is to limit the harmonic injection from individual customers so that they will not cause unacceptable voltage distortion for normal system characteristics. And they limit the overall harmonic distortion on the system voltage supplied by the utility. It also specifically notes the objectives of the current limits are to limit the maximum individual frequency voltage harmonic to 3% of the fundamental and the voltage THD to 5%, which, by the way, for medium voltage systems, those are the limits for the voltage distortion. So you can see where this is all fitting together. As long as we're simulating and looking at systems that don't have a parallel resonance or some oddity like that going on. We're talking about a simple inductive system. Continuing, the current distortion limits are developed assuming there'll be some diversity between the users who are injecting harmonic currents. This diversity can be in the form of different harmonic components being injected, differences in their phase angles, their individual levels of harmonic current. And often what we see is the lower orders have less diversity, and the higher orders tend to have even increasing diversity because of their phase. So in recognition, the current limits are developed so that maximum individual frequency harmonic causes by a single customer will not exceed the limits in table 10.1. And this table is shown here below. So in table 10.1 in the 92 version of the standard, notice that despite them saying here, we want to limit to 3% and 5%, in reality, they're saying, well, let's get a little bit more strict. This is how we're going to include diversity. Let's get a little bit more strict on the limit based on what the customer relationship is. In other words, what type of customers do we have on the system? And what is the short circuit ratio? That's this value that we're going to look at in terms of defining plant size versus grid stiffness. And so here we see that the amount of individual frequency harmonic voltage is decreased based on the plant becoming more and more of a significance here when we get more diversity. So see the related assumption: dedicated system, 1 to 2 large customers, a few relatively large. Now, these are rather general terms. They're not very specific in terms of what they did, but this is giving you the indication of how they incorporated diversity within these systems. And they assume that for a system when the short circuit ratio gets really big, it's a lot of medium-sized customers or smaller customers, just a lot of them, versus a more dedicated system condition. So this is the basis that's presented in the 92 version of the standard for where they came up with the current limits. And in summary, it assumes a typical system characterized by simple short circuit, which is not necessarily reality, but that's the basis. That's the basis. It assumes there's no resonant conditions, assumes there will be diversity between the injections. It limits the maximum individual voltage distortion to 3% while incorporating diversity and plant size, and limits the total voltage THD to 5% while incorporating, again, diversity and plant size. There's a critical caveat. This also means that we can have violations in voltage if there's a sufficient lack of diversity. Both the 3% individual 5% TH limits can be violated when all users are meeting their current limits. If there's no sufficient, if the diversity that was included in creating the basis is not matched. So for those type of conditions, we need significant coordination between owner, suppliers, and users. And this is specifically noted for us in the 92 version. In the 2022 version we have, it talks about shared responsibility. But this is where the basis came from, and it notes clearly that we can have conditions where you could have a violation, the utility grid, or the utility responsible for the grid distortion may actually be in violation while every one of the clients and every one of the users are meeting their distortion limits. And when those conditions happen, everyone needs to come together and see how they're going to address the problem. Do I have a suggestion on how to do that? No, I think it's going to be system dependent. I think you'd have to really evaluate the system. A couple more observations. A careful inspection of the harmonic current limits will reveal that they are somewhat based on the characteristic of a 6-pulse rectifier. You'll see how they get lower as you go higher in frequency. And this is very characteristic of a 6-pulse rectifier. And I think that probably was done on purpose. I mean, you have to think about it. Of course, higher frequencies, you want less and less of them. That's true. But at the time that the 519 current limits were brought about in 92, it would have been prudent to supply limits, or it would not have been prudent to supply limits that caused all the users with 6-pulse VFDs to be out of compliance upon release of the standard. So if you look at the standard and you see how it looks historically, you'll notice that characteristic. And in addition, in the 92 update, it also includes a limit increase for large rectifier installations that utilize multi-pulse arrangements. And I know for a fact that the reason why that was done was because a particular engineer by the name of Alan Ludbrook, who's passed away since then, specifically negotiated this with Ray Stratford sitting in Atlanta at a hotel, because I was at the table. So there was an agreement that, well, if I'm putting in all these millions of dollars of multipulse arrangements to reduce my distortion, why should I be in violation of the 519? And so this square root of Q over 6, and now in the 22 update, they replaced Q with P. So square root of P over 6 for your pulse number gives you a limit increase that if you have a multipulse arrangement, you can take advantage of. So, and if it's not there, more than likely you would be in violation of the limits, even though you've reduced 5 and 7 and 11 and 13. You've reduced all these lower orders so significantly. It turns out keeping the standard without the square root of Q over 6 would have caused them to be in violation. So those are two things we could look at historically and say, okay, so that's why the limits look the way they look. Okay. We're going to jump into the actual limit tables now. Voltage distortion limits. Okay, at the PCC, owner operators have to limit their line to neutral voltage harmonics as follows. For the daily 99th, by the way, this is a measurement where 3-second values are accumulated for a full day. So we accumulate all those bins. My example was very trivial. I only had like 40 some. But imagine how many 3-second numbers you're going to need for an entire day. You're going to accumulate those for each harmonic over a day. Those, once you calculate 99th percentile for each one of the harmonics, the values must be less than 1.5 times the values in the table. For the weekly 95th, you're going to capture 10-minute values over an entire week. And at the end of the week, the 95th percentile shall be less than the values given in the table. So notice 99th percentile. By the way, percentiles are supplied so that we don't perform a compliance check on really short time, unreasonable numbers. That's the whole purpose for these. In other words, they want to say, well, yeah, you may have seen 10% voltage distortion, but it lasted for like 1 to 2 seconds. And it really doesn't affect the steady state operation of the facility. And so the whole idea of percentiles, 99th and 95th, is basically to say, well, let's look at the general, not average operation, but what's being covered 95 and are happening 95 or 99% of the time. That's why we use percentiles. And this, again, keeps a compliance check from kind of going sideways, where you take a measurement and someone says, well, you know, you had a distortion of voltage distortion or current distortion in excess of the standard. And you say, well, how long did it last? Oh, well, a few cycles. Well, let's take care of that. And so that's why in the 2014 version, we introduced percentiles, so we can take care of those unusual and really unnecessary conditions. All values have to be in percent at the rated, or excuse me, at the fundamental voltage rating. And table 1 applies to harmonics whose frequencies are integer multiples. We're not talking about interharmonics yet. We're talking in these tables about integer harmonic multiples of the power frequency and must be included up to the 50th harmonic. So here's the table. I'm sure you've seen this before. We don't need to go over it in great detail. 5% on low voltage systems, max 8, each individual less than 5. Here's the medium voltage one that most of us are familiar with, 3 and 5%. When you go up to higher voltages, 69 kV to 161, you're limited to 1.5 individual, 2.5% THD total. And for greater than 161 kV, no THD greater than 1.5%, and 1% for the max individual. Again, this is for owner operators to utilize. Okay, a couple comments. Once voltage THD and individual harmonic components are placed on a nominal voltage basis, that is when they can be compared directly against the table. My personal opinion, I'm not fond of the 5%, 8% distortion level for low voltage systems. That was modified in the 92 version. It was 5 and 3. 5% THD, 3%. So they increased this for low voltage systems, and I was not privy as to why that happened on the standard. So the reason why I don't like it is because in 1986, there was a paper by a guy named Cummings at General Electric that noted when you reach 8% voltage THD, you begin to experience additional heating in induction motors. And since induction motors are still very widely used, it just made sense to me that why would you push it to 8%? You know, when you know everyone is down on low voltage systems, you know, typically people are always pushing the limits. It's rare that you're going to find a location where people are always far, far underneath the limits. Almost all the time in application of the 519, you're going to find people are always pushing them, always pushing the upward boundary. So that means they're probably over 8%, which means you're having additional heating in your motors, which could become a problem. So I say stay away from it, keep it at 5%, 3%. But of course, the standard says what it says. And but this would be my professional advice. So also notice that the high voltage systems are strictly limited. So some utilities, when you apply a lot of these large new loads that are going in, okay, when you apply them to a system, they'll actually say you need to run a review and make sure that the voltage distortion of you adding your plant on is not going to exceed these limits. So they're going to have you do a performance check during your study work. And so these are very restrictive. And when the grid system itself happens to be filled with resonances, you may find this is difficult to achieve sometimes, but that's the goal. This is what we're shooting for, because we don't want high levels of distortion on the interconnected power grid. We just don't want it up there because there's, like I said, there's too many resonance points on an interconnected power grid with all the overhead line charging. It looks like a mountain landscape up there compared in terms, if you look at the impedance profile, it looks like a mountain landscape rather than just a simple single resonant point. You know, they could have multiple. I've seen impedance scans of grids that have 3, 4, 5 resonant points on them. So what does it look like? I just thought it for, you know, since we're going over distortion and all we're looking at are numbers, what do these look like? So if you have a 1% VHT limit, then, or, you know, if you want to see what 1% looks like, you know that the maximum individual can't be greater than 3 according to the standard. So let's assume we have fifth harmonic at 1%. And let's say to visualize 3% voltage THD, again, that's within the 519 limit of a 3% individual. So let's say the fifth harmonic is 3%, and that's all we have. Now, when you get to 5% voltage THD, the maximum individual, again, can't be greater than 3. But to achieve 5% voltage THD, you can get that in any number of ways. There's an infinite number of combinations here. But let's just choose 3 simple ones. 3% fifth, 7%, a 3% seventh, and 2.65% 11th. That'll give you a THD of 5.002. Now for 8% voltage THD, if you want to achieve 8%, look at this. This is kind of revealing in the table. And you want to keep within the 3% limit, which I believe has been upped to 5% in the actual limit table. Yep, it's been up to 5. But I wanted to keep it at 3 and generate more harmonic content, 3, 3, 3, 3, 3, all the way, and then 1. And with this combination of these percentages, I get 8% voltage THD. What does it look like? So here we go. So if you have 1% THD, you're doing really good. You look very sinusoidal. At 3% total harmonic distortion, just with fifth harmonic alone, you're getting a rather non-sinusoidal look here appearing on your voltage. When you go to 5% THD, this is what your supply voltage looks like with 3% fifth, 3% seventh, and 2.65% 11th. When you go to 8% voltage distortion, and these percentages for each of these harmonics, this is what the waveform could possibly look like. So you can see a reason. I mean, for me, visually, I would not want to see my system go over 5%. If you just look at this visually, I mean, this is looking like a mess here already. And this is going to be applied to every piece of equipment connected on this bus. For everything that's downstream. You know, distortion never goes downstream because no one's putting harmonic filters down there. At least most people aren't. So if you have 8% voltage THD at the point of common coupling, I'll guarantee you it will be greater than 8% further downstream. So I just thought this was a helpful slide. Okay, current distortion. So we're going to move now from voltage distortion into the current limits. The current distortion limit shall apply to a user's PCC, primarily with harmonic producing loads for installations with inverter-based resources. Users are going to be directed to use other applicable standards. So, but we're not going to discuss that today. We're going to discuss the IEEE 519 current limits. So for installations where there's a mix of both loads and inverter-based resources, the decision tree in this next figure will help you determine which standard you should be applying. And that basically says, do you have them? Yes or no? If yes, you do, then is the combined site-rated generation less than 10% of the annual average load demand? If it is, use the 519. If it's not, go to a different standard where you look at applying current limits that include in the high percentage of inverter-based resources. And what we're going to focus on now are systems that are fitting within this condition of applying IEEE 519 current limits. By the way, I don't think this table was in the 2014 version. I think this was added between 2014 and 2022. Current limit criteria. So there's 3 tables. And the first sentence in each of those tables, there's a lot of common content between these 3 tables. And so what I've done is I've broken out the contents that's different. And then for the stuff that's repeated over and over again, I've tried to keep it listed here only once. So the first sentence in each of the current limit categories is slightly different. And it's because of the voltage application. So the first table talks about the PCC connection voltage between 120 volt and 69 kV. So this covers all of your low voltage and medium voltage systems. The second table addresses systems between 69 kV and 161 kV. And the third table addresses PCC voltages greater than 161 kV. So where a lot of us will be spending our time is here. And then for those people who have really large plants and facilities that are directly connected up to a sub-transmission or transmission voltage between 69 and 161 kV, you'll be using tables 2 and tables 3. So the following criteria in these tables, up to each of the limit tables, these notes here are identical between the 3 tables, and they read, the limits shall not be used for the evaluation of an individual nonlinear load, but rather for the evaluation of the installation containing such nonlinear loads. At the PCC, users shall limit their harmonic currents as follows. So this is common for every single one of the tables. And common also is that they specify for each of the current limit tables, the daily 99th, the weekly 99th, and the weekly 95th. For the daily 99th, you're limited to values 2 times in the table. For the weekly 99th, 1.5 times the values in the table. The weekly 95th, the values in the table. All values, this is also common to every table. All values shall be in percent of maximum demand load current IL and shall be established at the point of common coupling. Table 2 applies to harmonic currents whose frequencies are integer multiples of the power frequency. Now, that's what it says specifically for table 2. For table 3, it'll just say 3, and for 4, it'll just say 4, because these are all common to each one of the tables. Again, we're looking only at integer multiples. When we want to go to non-integers or inner harmonics, we have to look at things slightly differently. And I have a section on that. Okay, so what time? We're 1 hour into this. I have about a half hour more of presentation and then example cases that we can look at. Okay, table 2. This is your first current limit table. Let's not go into diving into it, except to note you have ranges of harmonic values that have to be within these limits. You have to calculate a short circuit ratio between the short circuit strength and the maximum demand load current, and that tells you what row that you're in the table. Total demand distortion is the most rightmost column. The only caveat here for integer harmonics, and this changed, by the way, from the 2014 and 92 versions, those limited all even harmonics to 25% of the values in the table. Now that has been changed. For the 2022 version, for harmonics less than or equal to 6, even harmonics are limited to 50% of those in the table. The other even harmonics are limited to the values in the table. A few other extra things we can look at here, but that's basically the key for each of these tables. For table 2, table 3, and table 4. Table 4 has a bit less number of rows, only 3 rows, but everything else is basically remaining the same as to how you would perform your compliance check. Okay, after each one of these tables, there's a paragraph that follows, and that paragraph says, for interharmonic current components, non-integers, with frequencies that are not integer multiples of power frequency, users should limit the components to sufficiently low levels so as to not produce undesirable effects on the power system and the connected equipment. Wow, that's kind of, it's good to say it, but just understand that basically puts the onus on people performing the evaluation to make sure, hey, no problems happen. Whereas historically, the 519 has never said that. And even the 2022 update of the standard does not specifically say that, that you have to meet the 519 so that there are no undesirable effects. It doesn't say that. The 519 hopes that when you meet those standards, that there will not be any undesirable effects on the power system, okay? But there is no guarantee that if you meet the limits in the 519, that you won't have problems. It's just that experience has shown us that when we hold to the limits, most of the time, everything seems to work just fine. But this statement is interesting in that it's basically saying when you're looking at non-integers, you have to make sure that you don't produce any undesirable effects. Limiting values and appropriate statistical indices. Now, this is where I think this may be an error in the tables, and you can look it up yourself. Table 2 says should, 3 says shall, 4 says shall. You can figure it out if you want to look at it later. And appropriate statistical indices shall be developed on a case-by-case basis starting from the guidance of Annex A and considering the specifics of the supply system, connected user loads, and provisions. Let me just note here that if you're starting to work in the area of non-integers or inner harmonics, you have your work cut out for you, making sure you get the proper limit table or the limit curve to help you with this. Just understand, we'll look at it here in a minute. It's not as nice and easy as the application of the 519 limits directly. Multi-pulse limit increase. Again, this follows every table. Individual harmonic limits given in the tables may be increased by a multiplying factor when actions are taken by a user to reduce lower order harmonics. These would be, in most cases, multi-pulse systems. The multipliers given in the second column of table 5 are applicable when steps are taken. That table is here. This is taken right out of the 519. The multiplier is the pulse number divided by 6. And so you can see here that a straight 6-pulse rectifier, it's one, by the way, I added this row to the table in the standard for this webinar presentation. If you've eliminated 5 by 5 and mostly eliminated 5 and 7 by using a 12-pulse arrangement, then you can increase the limits in the table by 1.4, etc. So these harmonics, by the way, all multi-pulse systems will have residual harmonics. Even though you're trying to cancel 5 and 7 perfectly, there will be some left over. To use this multiplier, you have to limit these harmonic orders to less than 25% of the values in tables 2, 3, and 4. So if you're going to use multi-pulse arrangement, you can increase the multiplier, but you got to make sure that the harmonics that you're canceling are below 25%. All right. So in summary, all currents need to be compared that are, statistically determined, compare against the tables, must be in percent of maximum load demand. Table limits consider size of user versus strength of the grid using the ratio I short circuit over IL. We suggest using ANSI symmetrical momentary current for ISC. The current limits are broken into 3 tables according to PCC voltage level. Interharmonic or non-integer harmonics should be developed as recommended in Annex A, and we'll look at that briefly. Increasing limits for multi-pulse applications require canceled harmonics be limited to 25% of the values in the tables. So now I'm going to fly through this section. It's going to be in the slides for you if you ask for a copy of the slides and you get them. I'm not going to go into this with a lot of detail. What I would like to do is just page through this quickly and hit the summary at the end, okay? Because that kind of gives you the breakdown of this content in here. Of course, get a copy of the 2022 version, read it for yourself, and you'll come to some of these same observations that I'm going to be making for you. Okay, let's go down. And in summary. So, by the way, just to show you here, this is kind of what they're asking you to do for the harmonics that are interharmonics. They're wanting you to consider utilizing something out of the 2014 version that talked about the flicker limits from IEEE. And since the interharmonics right around 60 hertz typically impact flicker, which is a visible light fluctuation of an incandescent light bulb, just to put that in perspective here, they're considering that to be important to use for the interharmonics right around the fundamental. And then you choose some type of a limit, 0.3 or 0.5%, which is what they're doing here. They're saying for voltage distortion, it should not be above 0.3 for the interharmonics, up here 0.5%. Here's another example of a curve. This one's slightly different, or a different suggestion. And they discuss what this is about in the standard. And in suggestion 3, they're talking about signaling controls. In other words, imposing control signals on top of a power system for controlling equipment out. There, they want you possibly to use lower levels and then coming up with even stricter requirements as shown here in this suggestion 4. So summary, there's 4 suggestions supplied in Annex A, but they are not prescriptive. This is noted. That means they're not to be used like the tables are a standard. Annex A is not to be used like a standard. In other words, they're saying you have to do this. No, these are guidelines. These are not prescriptive limits. These are limits that we're suggesting. Any interharmonic limits determined must be based on specific areas and systems of application that are sensitive to interharmonics. If you don't have anything that's sensitive to them, then you can almost set the limits where you want to, according to this, okay? But they make a recommendation, of the 0.3, 0.5% consideration. In the IEEE, in the earlier versions, I believe they said interharmonics also had to be limited to 25% of the values in the tables. I know that was true for even harmonics. I can't remember if that was also true for interharmonics. I would just have to go back and look at the table. So the IEC flicker limit, though still based on an incandescent light bulb, has been recommended for interharmonics around the fundamental. Interharmonics is an area where general limits may not be appropriate. In other words, if you have a system that you're evaluating and it's got a controller, this is used predominantly, they list the different countries that this type of control is being used, then you may want to specify a very strict limit just for a small frequency range where you'd have this condition being. So general limits don't seem to be appropriate here, which they are utilized in the IEEE 519 limit for voltage and current. Those are general limits. If you have no detailed information on interharmonic sensitivity, in my opinion, use suggestion 1. I think it'd be better than nothing, okay? Regulatory application. So I'm gonna fly past this really quick as well because there's just a couple notes that need to be made. I've been involved with small municipals wanting to have content from the 519 put into their actual regulatory document because they have issues with clients who they're not aware. And so they're not aware of the 519. And so they needed help with this. And so I've seen it used. So my commentary on this. So this is my own personal commentary. The 2022 update of the 519 is now a standard and no longer recommended practice. So that has to be noted. This makes that means that it is particularly targeted, or that's maybe not the best word, but that it would be a reasonable fit for our local regulatory application. That would actually be a better way to say this. This makes it, and this should be it, not is, by the way. This makes the 519 particularly relevant for a local regulatory application. Even though the standard is well known to us and many of us in the electric power industry, many municipalities, small utilities, and companies, they are not even aware of its existence. And that's why using it for regulatory application seems reasonable. In such cases, adopting the 519 into their local codes is a form of education and building awareness combined with regulation that can serve them well. So the key is proper application. Remember, I noted how, because of the wording in the 92 version, drive vendors still apply it to their drives, which is not to be done. People still apply it on the inside of a plant. I had done a study less than a year ago where the PCC was defined inside a plant, and I disagreed, commented on it, but that was what was written into a contract. That is still being done today, okay? So proper application is mandatory. You have to know how to use the standard. You have to know what it is, what it accomplishes, where it's supposed to be applied, and even more importantly, where it is not to be applied and utilized. Education is pivotal if it's going to be used in a regulatory environment. Administrators will need to be provided training that present the complex engineering of harmonics in a ubiquitous, well understood language. Regulatory use should be pursued with great care, and it must include proper referencing and application of the standard. I think this is all common sense, but it's just important to note if anyone is considering that. Best practice. I'm sorry if I'm repeating myself, but I have to, just because this has been a problem across the industry. The 519 is not an equipment standard. It is not intended for use within plants. Must be applied at the PCC between owner-operators and users. We read the sentences out of the standard that say this. Okay, so this is how it needs to be applied. Owner-operators must meet 519 prescribed voltage. Users must meet IEEE 519 prescribed current distortion limits. When issues arise and all users are meeting limits, all parties need to work together to maintain quality of voltage of their shared electrical resource. Okay, applying the limits. I hope we have a little bit of fun with this. I have a couple examples I'd like to show you. Hopefully they'll be a little bit more entertaining than the dry running through of the standard and all of the limits and their basis and things like that. So in this, for applying the limits, when you do it, this is the methodology that should be utilized. Select the point of common coupling, determine what it is, determine maximum demand load current in amps at the PCC, determine three-phase symmetrical fault level at the PCC, calculate I short circuit over IL, find the table and row that matches your application, extract the limits, and use them for a compliance check. So, for a measurement, get a qualified meter that includes IEEE 519-2022 statistical evaluation. Perform the measurement for at least 2 weeks or longer if there's a great deal of load variation. But if you think 2 weeks covers what you consider normal operation, 2 weeks should be adequate. Actually, the standard says 1 week, but by the time you start and then you're covering a weekend, there could be variations there. I recommend a good 2 week measurement. It just helps you at the endpoints of a single week. Extract the measured 95th, 99th percentile harmonics and compare them against the limits. Include the limit multipliers for each of the statistical categories when comparing the measured values. So if you're performing a study, now, a little bit of difference here, because nothing is mentioned in the standard about applying it to a study. In other words, how do you do it? What approach should you take? So here's my recommendation. For study compliance, determine if your plant load is highly variable or of a constant nature. If it's fairly constant, model the system at its greatest level of harmonic production. Assume this will be the weekly 95th and use the limits in the table for your application with no multipliers. This is conservative because you're using the lowest limits. You're not multiplying them by 1.5 or 2, and you're assuming your load is steady, which, hey, that's what the standard is about, right? Steady state conditions. And then apply it as if it's the weekly 95th. If this is going to be a bit more work now for this next case, if your load is widely varying in nature, you're going to need to model the system, possibly using scripting of some kind to make this automated within your analysis at many loading conditions, which will be present over a day and over a week. Now, this is especially true if you take your maximum harmonics and you're exceeding limits. Okay, you see what I mean? If you have a maximum condition for a very short period of time, only a minute or 2 minutes or something, and it exceeds the limits and you utilize that as your compliance check, you might be over designing your system when in reality you would never be out of compliance. So if your load is widely varying in nature, you may need to model a variety of loading conditions over which are present over a day or over a week, and process those simulation results statistically to determine 95th, 99th percentiles and compare them with the limits with the appropriate multipliers. So in this second case, you're kind of mimicking how the plant would actually run in its varied nature. In the first case, the plant runs pretty much steady state and you don't need to consider varied nature. And you would end up with your 95th percentile being that value that you're actually, be that same condition that you're actually simulating. So let's look at 3 examples. A compliance measurement of an arc furnace, a previous distributed system analysis, kind of like a case study, and then I'm going to model one for you. And given it's about 20 after, I might go a bit over, on this. So I'm sorry if I'm going a bit long, but this is just a lot of material to cover. But I hope you find these entertaining. So let's take a look at the compliance measurement. So this is arc furnace at 13.8. Maximum demand is about 2,000 amps. The short circuit ratio is about 15, putting us in the first row of table 2. So let's look at a measurement and see how this actually may work. So with my frustration of power quality monitors, I made my own. And out of that, I have captured a number of conditions. This one is an arc furnace. And in this compliance measurement, I wanted to show you what I would want for a compliance check for IEEE 519. First, let's look at what the voltage and current looks like on this arc furnace. I'm going to play this back in real time. Actually, this is going to be played back faster than real time, if I can check the button correctly. Yep, skip the playback timer. And so what you're going to see is data going by very rapidly, okay? And for some reason, I am going to stop and start this. Again, for some reason, it's running extra slow. And I don't know why. It was running extremely fast before. Of course, whenever you get to do stuff, that's when stuff runs slow. Maybe it's because I have so many applications running. So let's look at this again. Let's see if we can get a picture. No, it's still running really slow. So I am going to move this into the arc furnace actually running. And here you see voltage waveforms on the top, current waveform on the bottom, and you can see the widely varying nature of this load. Okay? Can you see the reason why a statistical evaluation would be important for this type of a load? So this load is constantly changing. If we were to look at the RMS voltage and current, you'll see that it's changing dramatically. At times, the voltage even drops all the way to 80% voltage during operation of the furnace. So you can see the spectral content varying widely over here. It's mostly in the lower orders, but it's going up and down constantly. So what would we do, or how would this look for a 519 evaluation? So in that case, the way I like to see systems analyzed is I want to see on a graph the 99th voltage for the day, the 95th weekly for the voltage. For current, I want to see daily 99th, weekly 99th, and weekly 95th. Now, the way this is going to work, when I start this running back, the voltage for the daily 99th and the current daily 9th are automatically going to populate because a 3-second value comes very quickly. So my chart here is going to update in real time based on how the bins are accumulating in my probability function, and then it's updating and calculating the percentiles on a real-time basis. The table would then, at the end of a day, would be locked and frozen, and then that would be the daily condition. At the end of a week, all of the bin accumulations would be locked at the end of the week. So here, if we run the furnace through it, and we look at the daily 99th, you can see that it's updating itself as conditions are changing and as it's accumulating within the probability function and then updating the distribution calculation. So you can see here in this case that for the daily 99th so far, slightly higher distortion condition appeared. And now we're exceeding our limit. Here, the red lines are the limits. You can see that the total demand distortion is just over. We have the second harmonic over this limit. We have the fourth harmonic over this limit. And that's how I would want to see my answers. Now, right now, the weekly 99th has nothing. And the reason why is 10 minutes have not elapsed, right? So I have nothing to look at because I don't even have a measurement that can start accumulating into my probability function to calculate what the 99th and 95th percentiles are. But I do have a run up here from a previous, see if I can find it. Right here. Okay, so in this run, I actually ran it past 10 minutes, and now I have every single one of the tables filled in. And let me zoom in maybe a bit here. I have the daily 99th. That's in violation for voltage at several places. I have the weekly 95th. Isn't that interesting? Because 95th percentile means we're excluding more of the extreme values. So weekly 95th is within the limit. Daily 99th is not within the limit. And interestingly, you notice the limits are changing. So for the weekly 95th, 6%. For the daily 99th, I believe it's 7.5%. So the limits go up when you're looking at more capturing more of the extreme conditions. And here we have daily 99th, we're over. Weekly 99th, just one overage. Weekly 95th, we're back with several others that are over because the limits are dropping, right? When we finally go to the weekly 95th, this is the lowest limit, this is the next higher limit, and this is the highest limit available because the multiplier is 2 for the daily 99th. So that's an example I had here for an arc furnace installation. It's showing what I would want to see on a measurement for compliance using the IEEE 519. Okay, now let's look at a distributed system. Now this is a case study of a system that I've actually simulated and performed an entire analysis on. I needed data for a harmonic analysis, but using maximum recorded values. Remember what I said about percentiles, how they help us exclude unrealistic values that come and go. So I wanted some values to use for the current injections for my harmonic analysis. So the client used a Fluke 435, captured all 50 harmonics on a 30-second basis for approximately 22 days. This resulted in a spreadsheet with over 60,000 rows in it. And I programmed it with a macro to calculate the 99th percentile out of all of these 30-second measurements. And I found the 99th percentile for voltage and current. Once I had them, I could use them as results and put them into the model, and I could benchmark the model. The way you benchmark it, you put your current injections in, you see what voltage you simulate, and you see how close that gets you. I then used the model to recreate the aggravated distortion level caused when other capacitor banks in this distributed system were online, causing resonances. Then after that, I developed a mitigation. So for this system overview, it's a 25 kV system that has a main supply transformer that steps up to 69 kV. And for this application, the utility was complaining specifically about their distortion condition. The I short circuit over I load was very low and indicative of a weak grid connection compared to the size of the facility. This placed us in the first row of table 2. The 25 kV distribution system included a host, there's probably 20 different distributed capacitor banks all throughout this distribution network. And when they would come on and off, they would generate different distortion. For every combination of capacitors, you'll have a different resonant point and different resonant condition. So we designed a filter system that would work well for almost all of them, and then noted which particular conditions they could no longer use those switched capacitors. This was a really difficult problem to solve. So here's the measurement. So The measured currents are here. I took the currents, created a 99th percentile, and this is the spectrum that I ended up with for the 99th percentile. And what I did in my model, I went to all of the distributed drives and set them up with this current injection. And I distributed it around all the drives. This is the voltage distortion that resulted in my model. The measurement is blue, the simulation is orange. And you can see that the lower orders, even up to the 23rd to 25th, are doing a really good job. But up here, I discovered that there's a resonance issue that's actually being caused externally by the grid. These benchmark measurements were made with no capacitors on the distributed system for the client, but it was the grid that was causing this problem. And also diversity is kind of creeping in. In other words, when you get to higher harmonics, a lot of these are really canceling out, but we get higher values in the simulation. To accommodate the diversity and to understand that at the resonant condition, it's really, really difficult to get matches, by the way, in a simulation when you have a resonant condition. I modified the current injections and I reduced them, so I recreated the exact voltage profile between the measurement and the simulation. I then proceeded to use it to do a check. So for this condition, you can see that the fifth harmonic is out of compliance, so is the total demand distortion, and so are the 35th and 7th harmonics. But this was just the baseline condition of the system without any capacitors online. There was no aggravated condition. This was just their normal operating harmonics with a nice, simple upstream impedance. And you notice they're in violation here, but when you aggravate it, it gets extremely severe. So in this case, their distortion would go up over 12% for their total demand distortion of current, and they exceeded the 5th and the 7th, and the 37th was still it was above its limit. Okay, so apply some filtering. What do we get? So this curve looks a little bit different because it has multiple bars, and that's because I simulated several of the worst case capacitor arrangements that created problematic resonances. And in this case, you'll notice that total demand distortion, all of the harmonics are below, with exception to these two levels. And after extensive study, I determined that these were caused by the grid, that the amplification of these harmonics is a grid issue. And so we reported this to the utility. They accepted the mitigation alternative and said that this was their issue to solve if it occurred. Which is, see, that's how it's supposed to work. If the grid is responsible for something, they take ownership of that. If the user is responsible for something, we take ownership of that. And the problem with the system was the distributed capacitors cause resonance conditions. And those resonance conditions created an aggravated violation, which is here, and which was actually affecting the 69 kV grid. Okay, last one. Now what I'm going to do here is I'm going to run through quickly, as quick as I can, an actual system study. So here's my system, and what we're going to do is we're going to look at plant D down here, and we're going to say on plant D, how do we do a 519 compliance check? And I'm actually, though I have this already prepared in a spreadsheet, I'm going to do it by hand in front of you and show you what I would do. Okay, so let's see if there's any more information here. Okay, it's a 34.5 kV main distribution system. You see that. This is all 34.5. It steps up to a 230 kV, but we're not concerned with that because the utility owns the 34.5, and our plant D, is fed by a 10 MVA transformer here at 34.5. The PCC is right here. This is the point of common coupling because it's the place shared with other users. See, it goes down, they feed a whole bunch of other users down here. So here's our plant. Inside our plant, we have a couple transformers, we have a couple drives, and a motor and a load. A pretty simple system. We're going to perform the evaluation for plant D. It's 34.5 kV grid connection and PCC. The maximum demand load is 64.59. The short circuit current is 4894. That gives us an I short circuit over I load ratio of 75. This places us in row 3 of table 2. And let's continue with modeling. And what I'm also going to do is throw up Excel here so I can put information in it. Okay, here's my version of Excel. I'll just keep this up here. I will minimize it for now. Here's my system. So what are the things I need to know? I need to calculate I short circuit over I load. Now I've modeled this to the accuracy that I want. And if I go to my power flow simulation, I will notice that the current at the PCC is 64.59 amps. Okay, so IL is 64.59. I'm going to come back here and I'm going to go to short circuit focus and I'm going to calculate the fault duty up here. And it is 4894 amps. So it is 4894 amps. And this is I short circuit. I'm going to calculate now I short circuit over I load. And that is just very simply short circuit current divided by the load current. And that gives us our value of 75.77. Okay, so now we have our beginning. We know for this is going to be, we are 34.5, so the, the voltage, sorry, keep typing that wrong, is 34.5. That puts us in table 2. And we, in terms of the row, we're going to be put in row 3 because of this I short circuit over I load value. Now, remember, this is the basis. This is your basis right here that you're going to percentize everything. Now, when I use Easy Power, I don't like to pull answers out of here in percent or per unit. I like them in amps. Then I like to put them on my basis that I define for my 519 evaluation. So I'll come to the harmonics program. And I have, by the way, oh, we can take a quick look down here. This is an adjustable speed drive. It's actually a 12 pulse. Okay. And if we look at the harmonics tab, we can see that 11th and 13th have significant components and the others don't. This is 12 pulse drive. This is 6 pulse set of drives equivalent with 6 pulse spectra. So up here, I'm going to run harmonics bar chart. And in the bar chart, I'm going to grab out of it harmonic. I'm going to grab these 2 columns. This tells me the current distortion is going up to the grid. Okay, this is the harmonic. This is my current. And this is the no mitigation case. And it is in amps. Now, I want this in percent of my basis. So I'm going to say this is equal to this value divided by $B, $3. And I'm going to update this. There we go. Now, oh, do you know what? I made a mistake. I didn't multiply by 100. If I want to compare in the table, they have to be in percent. There we go. Now, by the way, some software packages will do a lot of this for you automatically. Me personally, I do it myself in my own table, looking at my own limits and my own base and everything that I evaluate on. I even have other spreadsheets that include a drawing. They will draw the graphical image of the limits over the top of these. Okay, so now we have without any mitigation. And what we want to do is compare this against the IEEE limits. Well, let's do that. Limit. So where are the limits? They are here. Let me escape out of this. Let me go back up to here. We are in table 2. I'm going to make a copy of this. Control C. I'm going to put it right here in my spreadsheet. I'm going to grow this. So for my limits, they are, we're skipping fundamental. We don't care about fundamental. Between the second, we're in row 3, between 50 and 100, so it's 10%. For harmonics, less than 6, even harmonics are limited to 50%. Okay, so that's 5. So this one's 5%. This is 10%. 5, 10, 5, and we stop at the 11th harmonic. So then we go 10, 10, 10, 10. Okay, and the 11th is in the next category. So the limits that I've applied are for even harmonics. Again, h less than or equal to 6, 50% of the values in the table. So that would be 2, 4, and 6 are half of the value, and then the rest of the values are 10%. Then the next category is 4.5, and that goes between the 11th and the 16th harmonic. Then the next category, it's 4 point, and if I make an error, you have to speak up and help me here. 17 to 22, and then the next category is 1.5 between the 23rd and the 34th. There we go. And then the last one is between 35 and 50, and that will be a limit of 0.7. 0.7. Okay, so for our compliance check, let's move this over to the side, and we'll call this limit, and let's take these two here. Insert, chart. What do we have? Oh, look at that. So now this is a quick and dirty way of comparing the limits versus the values. And if you see here, we're in compliance with exception to the 11th and the 11th and the 13th are out of compliance. And we're just borderline on the 35th, 37th, and then this value up here, which maybe is the 40, 45, 46 something. We're just out of compliance up here. So we need some mitigation, right? We need to get these within compliance. I could have created a condition where these are greatly over, but this is good enough. We're showing that we're out of compliance and we have to do some form of mitigation. So I will call this case no mitigation. Now I need to design a filter, or by the way, there's 100 ways to mitigate, but filtering is often the common one used the most, okay? But you can move loads around, you can relocate loads, you can take capacitor banks out of service, you can change capacitor bank sizes. There's lots of different methods for mitigating, but often on a system that we know it has a problematic condition with no resonance present, you need some form of filtering to absorb it. So I'm going to make a copy of this. And here, with mitigation, I am then going to apply that to my case. And by the way, when I selected this line and hit bar chart, what it did was it gave me the harmonic currents over that line. This is the PCC. And so I wanted those currents at the PCC, and this is where it's located at the top of this transformer. So that's the action that I was taking when I clicked on the line and then clicked on bar chart. You can do the same thing for voltage. You can click on this, the bus, and you can click on bar chart, and you'll get a bar chart for the voltage distortion. But I'm not interested in that because I'm doing a current limit compliance check. Now that I've got the system, it turns out, I will show you here that I've designed a filter that is a high pass filter. It includes a 3 ohm inductor. This is tuned around the 5th harmonic. And it has a 10 ohm damping resistor. And this is a 3 megavar bank at 13.8 kV. So what I've done here is I'll turn this on. Now this is in service, and I will do the same bar chart. I will grab this value here, copy it, and I will replace the value in this column here, right here. And there we go. So this is with mitigation. So here we have now, we have the limit in orange, and we have the harmonic production still on demand, iLoad on demand, and you can say that with that filter, we accomplished. Now let's flip between these two charts. They should be sitting in the same place. So this is without, this is with. I feel like I'm doing a optometrist test here. This is without, this is with. So we have brought all values close to an exceedance, borderline, and this one definitely over, within compliance by applying a high pass filter. Now, in reality, I would design that as a C high pass, so I would eliminate my 60 hertz fundamental losses in the resistor bank, but it's going to produce the exact same result in terms of absorption. So I did that quickly so that I wouldn't have to go into all the extra details for a C high pass design. Okay, those are the examples that I wanted to show you, and that, as you know, I've reached pretty much the end part of the presentation, and we can open everything up for questions now. So we're looking at the chat, Wes and myself. Just let me know, if there's any questions that you might have regarding the presentation.
Nice job, Chris. Thank you very much.
Oh, definitely. I hope everyone stayed ready.
I'm sure they did. Looks like we already have a question there.
Okay. IEEE 592 only in current harmonic section. It indicates that IEEE is not applicable for, yes, inverter-based resources. In voltage harmonic limits, there is no IBR mentioned. Does it imply that IBRs still need to comply for voltage harmonic limits at the PCC, or only the system owner shall be? The last half of your question, it would be correct. It would imply that owner-sister operators are still obligated to meet the voltage harmonic compliance at the PCC, regardless of what's happening on the current limit. Yes, I would agree, and how you answered that kind of yourself there at the end. Mm-hmm. Any others? Regarding a harmonic filter, is it possible to have a high-pass filter, harmonic filter installed to filter out all higher-order harmonics starting from the second harmonic through the 50th, or such high-pass harmonic filters too costly to build? Okay, in my experience, okay, so when you come to high pass or C high pass filters, there's a compromise. The greater the damping you supply, which helps you absorb some of the higher harmonic content, the less you're able to absorb its fundamental tuning point. So if you make a fifth high pass filter, it's a notch filter combined with the damping resistor. In that case, the more you are making it able to absorb higher frequency content, the less you're going to be able to absorb the fifth. It's compromising the filter. And so you have to go through kind of an optimization. There's no filter that will absorb on typical distribution systems like 34.5. There's no filter you can apply that will do a broadband absorption. Now, if you remember historically, and I don't think these are being made anymore, there were low voltage broadband filters that were created a number of years ago. And I don't know if they're in application, if they're still being sold. But what those filters did was they combined an upstream isolation reactor with a very broadband filter to absorb all of the harmonic content of the drive. But the problem was the isolation reactor has to be very, very significant impedance so that the harmonic currents will favor going into the broadband filter, go into that filter component rather than heading up out through the isolation reactor. Those I actually measured some a number of years ago, but I've never seen anything applied like that on a medium voltage, only on voltage. And then again, I don't even know if it still exists. I hope that helps. IEEE 519 is applicable for PCC. Is there a standard for generator given higher impedance of generator? Is there a standard for? Could you give me some more clarity on that? The question you're asking? Is IEEE 519 applicable to solar farms? That's where you're going to have to take the 519 and look at that chart and see what your penetration is compared to any other plant. So if you're a standalone solar farm, it appears from the 519 that you really have to correlate to a different standard. However, I would note there are contracts, there are agreements that are in place still where utility suppliers are requiring that the solar farm meet IEEE 519. I just did a wind farm that all of the wind turbines are using inverters. And in that case, this was up in Canada, and there was still a requirement that they meet the IEEE 519 at their PCC. So you see what I mean in terms of people writing things into contracts that they want. And so your requirement is to meet their contract. So I've seen it applied both ways. Since we are not user but inverter-based producer, yeah, that's right. Greater, greater than 10 megawatts. Standard of harmonics for generator. The only thing that I am aware of, I know that I'm certain that there is a standard for harmonics produced by generators in the, holy cow, can I remember what it is? It's the MG1, that standard MG1, I believe. If you look in there, it will discuss limits for harmonic production by generators. And this is especially the case for smaller generators in the 1 to 2 to 3 megawatt size, that you will find that the line to neutral voltage is highly distorted due to the winding pitch not being as fine. And so I would think you would refer to standard MG1. Okay, for harmonic measurement, is there any minimum required recommended total measurement period, a week, a month, or more? If the harmonic measurements during the specific harmonic measurement period pass the IEEE 519 limit check, could we conclude the installation is in line with 519 harmonic requirements? So as far as length of time, there is a bit of subjectiveness in the standard. They say do a week check. Now, they're expecting you to consider that you're going to monitor every week from the beginning to the end. You see what I mean? So they're saying they don't want you out of compliance ever over any period. So it's going to be engineering judgment for you to determine when do we think that worst case condition is occurring within our plant, and you have to make sure you measure a wide enough time frame so that you get in what you consider to be your worst case harmonic loading conditions. And I would note, and I'm sorry this is this subjective, but what happens is the statistical evaluation makes it a little bit funny, doesn't it? When we looked at my measurement on the arc furnace, hey, one of them was met, one of them was not. And that's because during the measurement period, due to the wide variation in the load, in my case, it was a wide variation in the load. In that case, you could find yourself in violation in one category and not in the other because of the variation. If your load is fairly consistent, like I noted earlier, as long as you consider all drives on, worst case harmonic production you can think of, all harmonic load at full load, fully operating, then and you do like a 2 to 3 week measurement, I think you can say that probably represents how the plant operates at the worst case for the rest of the year. Okay, how do you go about determining what a proper compromise in when you evaluate a system? Would you elaborate on what you mean by compromise? Compromise of what? The limits? So could you talk about systems that have wide swings? Say in a 200 megawatt plant, 180 megawatt would be for 80% of the time loading, where 20 megawatt would be for 20%, and where 20% startup loading for idle for high harmonic content. So I would evaluate each one. I would, if I considered those to be viable operating conditions for long term, greater than a day or a week, I would simulate each of the different loading conditions and make sure that I was compliant within them. Again, are they operating 200 constantly and then go to 180 constantly? Or is it changing dynamically between 200 and 180? You see where I'm going with that? So you'll have to think, about how you want to apply that. I'm sorry, on the compromise question, is there anything that you can offer on how do you go about determining what a proper compromise is when evaluating the system? Can you give me some, elaborate on what you mean by compromise? Then I can answer that question. Yes, David, you're right. It is a lot of work when you have these wide variations, and you have to utilize your engineering judgment on that. I understand your condition there. I've had to wade through. There's a couple other things that you have to wade through too, and that is, what do you do if you have a plant that has 3 individual connections? Hey, do you evaluate each one individually, or do you take them back where they tie up to some common point if they come together? Where is that point where they tie together? Sometimes the PCC is difficult to locate. I have on cases where I know that a industrial plant with 2 individual feeds eventually ties together somewhere upstream. I have evaluated the PCC by putting in a fake branch in my simulation model and evaluating as a total plant condition rather than 2 separate PCCs. So definitely, yeah. In your presentation, you talked about compromise with owner utility. More just a generic question when a client asks you to evaluate a system they're having a problem with. So in terms of people working together between owner operators and users, I could see owner operators compromising and saying, you're at 5.3, we're at 5.3, you're the biggest user on the system, we're doing okay. So for instance, I had one case where the voltage distortion was within the criteria, but the user was in exceedance by 300%. But they were the only user on the system at the time. Kind of see what I mean? Or there may have been 1 or 2 other people on there, but the voltage 2 or 3 other clients, but not big. They were small. And so in that case, a compromise was made. The utility said, well, we're not going to do anything until we see the voltage distortion start to get too severe. Then we'll start limiting individual users down to the 519. So that was a compromise that was reached between owner operators and users. I hope that was a good example. Any other questions? Yes, thank you. It just seems like a case-by-case basis. Yes, that is correct. It is. Every single evaluation is case-by-case, I would say. I have not come across too many installations that I've modeled and simulated where they matched really close to something else that I did. A lot of this is because of the grid connection being so variable. Distribution systems, who knows where every distribution is based on geography, where things are located. And so every place that you interface with, the short circuit current and is going to be differing and changing depending on the particular grid that's upstream. All right, we're at our time limit of 2 hours. And any last questions before we wrap up? Okay. All right, Wes, I'll let you close us off.
Excellent. All right. Well, everyone, if you do think of a question later on or something that we haven't gotten to yet, you can certainly email me and I will forward those to Chris. And also, again, if anyone needs any PDHs, we're happy to certify that you attended the webinar today for the 2 hours. Just email me with those requests as well. And that'll be it for us today. Thank you so much for coming. And thank you, Chris, for your presentation. Looks like a lot of people enjoyed it.
Great. Excellent. Thanks, everyone. Take care.
Thanks, guys.